In today's lesson, we're going to practice and consolidate some of the ideas that we came across last lesson in network flows. So last time we came across the idea of a cut through a network. This was performed using the capacities on each arc, and a cut was calculated by adding together the capacities of any arc that travelled across that cut, as long as it was travelling from source to sink. The rule for a cut is that it has to be a line travelling through arcs only, and it has to separate the source from the sink. We found that the value of a cut was an upper bound for what a potential flow might be through a network. So the smaller the cut, the better, because the value of a cut is saying the flow can definitely not be any higher than this number. So we get more information if we've got a small number for that. Then the maximum flow minimum cut theorem says that if we can find a flow that equals the value of a cut, then it must be that must be the maximum flow. So here, if you can pause the slide, calculate the value of each of these cuts, and then unpause. So the values, cut C1, which can be written in set notation as SAC and then BT, has a capacity of 20. Cut C2 has a capacity of 18. And cut C3 has a capacity of 16. Remember that only the capacities of arcs that travel from the source side to the sink side of the cut are included. We don't include any that travel from sink to source. So we're now going to do an example using the maximum flow minimum cut theorem. So we're going to start by trying to find a potential flow as high as possible by trial and error. We're then going to try and find a cut that matches that. So pause the slide now and try to find the maximum possible flow that could travel through this network from S to T. So we could start by saying, well, if we were to travel along the path SCT, the maximum flow along there could be 4. So we could have 4 from S to C and 4 from C to T. Now, although CT does have a higher capacity, we are limited by the fact that SC only has a capacity of 4. So we could then consider S to B to T. We could that is restricted by the capacity of SB being 3. So we could put 3 along S to B and 3 along B to T. We could then consider S to A to T. So that is restricted by 5 along AT. So we could perhaps put 5 along SA and 5 along AT. We now need to consider whether we can increase this a little bit. So I can see that S to A could increase by 1, A to B could increase by, well, more than 1, but definitely 1, and B to T could increase as well. So potentially we can now actually make S to A 6. We could have 1 travelling along AB, and we could increase BT to 4 instead. So we're just going to keep considering whether we can go any further. Now I can see we can't go any further here because all of the arcs coming out of the source S are now saturated. They're now at full capacity. So there's no way that we can increase any more of the flow through this network, even though there are still some arcs that could potentially be increased. So that's a maximum. So the flow we have found here, the easiest way to calculate the current flow is to add up the values coming out of the source. So 6 plus 3 plus 4, so that's 13. We can also just check that also works going into the sink. So 5 plus 4 plus 4, that is also 13. So we've found a potential flow of 13. If we can now find a cut that also has a value of 13, then that will tell us that we've found a maximum. So in order to find a cut, it's always good to try to look through any saturated arcs, because that is where the minimum cuts tend to be. So actually, if we use this cut here, so this cut would be S on one side, and then A, B, CT on the other. That has got a value of 6 plus 3 plus 4, which is 13. So we could say that by the maximum flow minimum cut theorem, we have proven that the flow we have found is a maximum. Now please complete the additional exercise questions on network flows.